All right, in this section we're going to talk about cardinality of infinite sets. When you're talking about finite sets, cardinality is easy. The cardinality of a finite set is just how many elements are in the set. But when it comes to infinite sets, it might be surprising that there are sort of different types of infinity that an infinite set can have the cardinality of. So let me start with the notion of having the same cardinality before we get into sort of different types of infinity. All it's going to mean for one set to have the same cardinality as another, it means that there's a bijection between the two sets. So this is totally what you would think if you're talking about finite sets, right? If you've got two different sets that both have 4 elements, you can set up a one-to-one onto correspondence from one set to the other. But this is the same principle for saying that one set has the same size as another with infinite sets as well. So the notation for has the same cardinality as is borrowed from our sort of absolute value cardinality notation for finite sets. So when I write absolute value x equals absolute value y, where x and y are sets, what I mean is that x has the same cardinality as y. And again, formally, that means there exists a bijection from x to y. It doesn't matter whether you say x to y or y to x, because if you have a bijection from x to y, its inverse is a bijection from y to x. Okay, this notation right here is something a little bit weaker. This is read the cardinality of x is less than or equal to the cardinality of y, and it's a statement about maps as well. It's the statement that there is a one-to-one function from x into y. And now be careful here, because absolute value of x is not yet even defined as some sort of number when x is an infinite set. So when I read this, I know it looks like an inequality of numbers, but it's not. This is the symbols that is representing right now there is a one-to-one function from x into y. Okay, and then this symbol, similarly, is not a statement about numbers. It is a statement that there is an injection or a one-to-one function from x to y, but there is no bijection from x to y. Okay, and this last expression right here, of course, is equivalent to x is less than or equal to y, and it's not the case that x is equal to y, because it is literally those two things put together. Okay, and it turns out that when you're sort of talking about two infinite sets having the same cardinality, sometimes it's hard to find like a straight up bijection from one set to another. It takes a lot of work to do so. But what's easier is to find an injection from x to y and then an injection from y to x. So the Schroeder-Bernstein theorem says that doing that second option is equivalent to the first. So written out, and I know you're looking at the theorem saying, duh, if x is less than or equal to y is less than or equal to x, then x is equal to y. That's not what this is saying, right? This is a statement about maps. This is saying if you have an injection from x into y and an injection from y into x, then you have a bijection from x to y. And it's actually not a super trivial theorem. It's sort of hard to weave back and forth between the two supposed injections and create from that a bijection. But anyway, the theorem is true. We're not going to go through the proof, but if you're interested, you can look it up. I just want to go right to studying some infinite sets and sort of measuring the difference between cardinalities of infinite sets, or the sameness of cardinalities of infinite sets. Okay, so in this example right here, I want to make the observation that the set of even natural numbers, so that's like 0, 2, 4, 6, 8, and so on, definitely an infinite set, and the natural numbers themselves have exactly the same cardinality. And this might be like the first surprising result about cardinalities of sets. On one hand, it seems like the natural numbers as a set is twice as big as the even natural numbers, but cardinality-wise, they are exactly the same. And that's because I can create a bijection from one to the other. Okay, so it's very easy to verify that this function is one-to-one and onto. In other words, it is a bijection. So we get from that, just by definition, that the cardinality of these two sets are the same. And we can even go further, something like this. The integers, so let's sort of write them out as an infinite set sort of in two directions. Again, it sort of seems like the integers set has twice as many elements as the natural numbers set, but it's not any bigger in cardinality. These two sets have exactly the same cardinality. Now, I can go through and try and write a bijection out formulaically. Sometimes that gets a little bit annoying to get the numbers right. It wouldn't take too much time, but you totally could do that. I want to give you a geometric way of sort of arguing that these two sets have the same cardinality. So let me scoot this down and sort of draw on the integers for a second. So what I want you to imagine is that the natural numbers, they start at 0 and they count up 1, 2, 3, 4, 5, like this in a line, right? And a bijection can be described geometrically by sort of matching up the nodes on this line with this set, which is the integers. So I'm just going to sort of wrap this blue arrow around and sort of give you visually the bijection. So I'm going to start it here, and then I'm going to move over to 1, and then I'm going to bend around and move to -1, and then I'm going to bend around and move to 2, and so on, like this, kind of stretching as I go. So this geometric picture is a description of the bijection that I'm defining. And you notice the pattern right away. So, okay, I've kind of run out of room, so you just kind of continue on in this manner. What am I saying? I'm saying to create the function f, actually I think I've created the function going from n to z more naturally, so let's write it like that. This is what the function does. It takes the input 0 and sends it to 0. And then it takes the input 1 and sends it to 1. And then it takes the input 2 and sends it to -1, 3 to +2, 4 to -2, 5 to 3, 6 to -3, 7 to 4, 8 to -4, and so on. So as you sort of traverse this blue ray, you're counting the natural numbers, 0, 1, 2, 3, 4, 5, 6. And as long as that counting exhausts the entire natural numbers as it goes, which it does, and also covers the set that you're counting completely, which here I understand from the picture that I will exhaust all the positive and negative integers, then you've sort of given a geometric picture for the bijection. And this is considered pretty mathematically formal. I know it seems like a little too hand-wavy, but there it is. And it also might even help you build a formula for that bijection if you wanted it. Okay, so there are just as many integers as there are natural numbers, is what I conclude from that. Now, this right here ends up being pretty surprising. So the rational number set seems to have like way, way, way more numbers in it. As a reminder, the rational number set is the set of all numbers that are ratios of integers, the bottom one obviously not being 0. And, if you imagine the rational numbers like written out on the real line, there just appear to be so many of these, like if you're drawing a bunch of rational numbers on a real line, between any two numbers on the number line, there are rational numbers in between. In fact, there are infinitely many rational numbers in between. So there are just so many rational numbers. It's kind of hard to believe that there is a bijection from the rational numbers to the natural numbers. Getting that formulaically is a giant pain, but I'm going to use the Schroeder-Bernstein theorem together with just a picture to argue that this is the case. So first off, I know that there's a one-to-one map from n into q. So any natural number is already a rational number. So this is a perfectly good map, and it totally is one-to-one, right? So I know from that the cardinality of the natural numbers is less than or equal to the cardinality of the rational numbers, right? That's the definition of this statement right here. And then what I'm going to do now is I'm going to define G from Q to N by a picture. And we're going to see that it's 1-to-1 from the picture. And so then we'll just invoke the Schroeder-Bernstein theorem and conclude that these two sets have the same cardinality. Okay, so let me draw the rational numbers, and then we're going to sort of use our ruler, our blue ruler technique to define G by the picture. Okay, so what I've got in this picture is a picture of all of the rational numbers. And the organization goes like this. I put all of the rational numbers that have denominator 1 on the very bottom line, so those would just be the integers. And then on the second line, I put all the rational numbers that have denominator 2, then 3, then 4, then 5, and so on. So think of your favorite rational number and find its denominator row, right? And then find the numerator in the column. And of course, I've got the alternating positives and negatives, so every single rational number is represented in this picture. Okay, so now I want to show you how I'm going to map Q into N in a one-to-one fashion using, again, this sort of like ruler. So I imagine having N represented geometrically as a blue arrow with dots, right? So this corresponds to the natural number 1, 0, 1, 2, 3, 4, like this. So I'm going to start the line right here, and I'm kind of going to zig and zag my way through the diagram. And notice that as I'm traversing the picture, I am picking up every single rational number regardless of its row and its column. So like eventually my blue squiggle will reach out horizontally as far as I like, and it'll also reach up as far vertically as I like. So if I use this sort of method, I will cover all of the rational numbers. Okay, well now what about the injection? How am I going to define the injection from Q into N? Because I don't know if you noticed in the picture, but that some of the rational numbers are repeated. Like right here, I have the number 1/2. And right here, I also have the number 1/2. So as far as defining the function G, this is what I would do. I'd follow my line, and I would look at the number, the rational number that I'm at any given time, and I'd say, okay, have I defined the function value for that number yet or not? So for example, the rational number 0 is here in my lattice, and I have not yet defined G of 0 yet, so I'll define it to be 0, the very first natural number. And then when I move over here, I'm looking at the rational number 1. I haven't defined that one yet, so I'm going to define it to be 1. So I draw a little dot there. And then I move over here to 1/2. 1/2 is going to be 3. Wait, 0, 1, 2, 2 rather, so 0, 1, 2. 1/3 is going to go to 3. And then I move over here. Have I done negative 1/2 yet? Nope. So G of negative 1/2 is 4. Down here to negative 1. G of negative 1 is 5. Go over here to 2. I'll get to a repeat eventually. That's what I'm waiting for. Okay, and then I'm going to come over here to 2 over 2. You see, I've already defined the function value at 2 over 2, all right? I don't want this function to be not well defined. So I'm going to skip over 2 over 2 because G of 1 is already defined to be 1. But that's no problem. I just skip over that and go to the next number. So G of 1/3 is 7, and you just continue in this manner. So in this way, you are coming up with a perfectly well-defined function that takes every single rational number, because every rational number is in this lattice somewhere, to a unique natural number output. So the natural number output that you're selecting is whatever dot that you're at that point. So this is our sort of mathematically formal proof that the rational numbers have the exact same cardinality as n. So it might be surprising, but there it is. Even though like Q looks a lot bigger than n, it almost seems like one dimension up from n, it has exactly the same amount of elements in this way as the natural number set. Okay, so let's start digging a little bit deeper into infinite cardinalities then. So we've seen a couple so-called countably infinite sets. N is a counted, so the book calls it Z plus, but I just call it N. And I don't know, I think I put 0 in the natural numbers. Maybe the book doesn't put 0 in Z plus, but whatever. We're talking about the counting numbers. They are countably infinite. 2n has the same cardinality as n, so that's a countably infinite set. Z is a countably infinite set. Q is a countably infinite set. So any set that can be bijected onto the natural numbers is called a countably infinite set. The finite sets are even smaller than that. Of course, you will not be able to biject any finite set onto an infinite set. But if you put the countably infinite sets together with the finite sets, you're talking about countable sets. And then it turns out there's a whole class of other sets that have like even more elements than countably infinite. And let's go ahead and I'll convince you actually in 2 different ways that there are sets that are like a bigger infinity than the infinity we were just talking about with the countably infinite sets. Okay, so this theorem is due to Cantor, and it's a very, very famous and interesting theorem. It uses a proof by contradiction, and it's somewhat unsatisfying. So you kind of have to read it like a few times before it really sits well with you. But anyway, this is how we're going to do it. So I'm going to prove that there are more real numbers between 0 and 1 than there are natural numbers. And from this, I'm going to conclude that the cardinality of the entire real number set is bigger than the natural numbers. So what I'm going to prove is there's absolutely no way to get a bijection from n onto the real numbers between 0 and 1. And if there's no bijection from n onto those numbers, if there's no onto map, well, no, that's what I want to argue. I want to argue that there's no onto map from the natural numbers onto the real numbers from 0 to 1. And from that, I conclude there's no way there's a bijection there. Okay, so suppose that G is an onto map from the natural numbers onto I. I is my notation for the real numbers in between 0 and 1. So I is this interval right here, 0 to 1. Okay, so I will derive a contradiction, and from that I will know that there's absolutely no way that there's a bijection from n into I, so there must be strictly more real numbers than there are natural numbers. The reason I'm getting that conclusion, of course, is there's definitely an injection from n into I. For example, something like this. This is 1 to 1. So we absolutely know that this is less than or equal than the cardinality of I. But what I'm showing over here is that there cannot possibly be a bijection between these two. So there must be strictly more numbers in between 0 and 1 than there are natural numbers. Okay, and this is Cantor's so-called diagonalization argument. Okay, so I suppose by way of contradiction that this is an onto map. So from this, what I'm going to do is I'm going to use this function g to give some names to the numbers in between 0 and 1. So I'm going to let an stand for the real number that's in between 0 and 1 that is hit by the natural number n, all right? So just a sub n is standing for that output of the function. And remember, this is an onto map, so every single number in this interval is some an, all right? Now, listen, the an numbers are real numbers, right? So they have decimal expansions. Okay, so A0 is some real number in between 0 and 1, right? So it has a decimal expansion that starts with 0 point, and then it has a bunch of decimals, right? So in order to like name all those decimals and all the decimals of all the ANs, I'm going to use a double index. So I'm going to write it like this. Okay, so A00 is the first decimal of A0 when it's written out. And A01 is the second decimal place, A02 is the third decimal place, and so on. Okay, I'm just going to then write out all the decimal expansions for all the ANs Okay, again, what have I done here? I've assumed that I have this onto map from the natural numbers into the unit interval 0 to 1, and I'm using the notation an to stand for the image element of n under this function. So the an's are a bunch of real numbers in between 0 and 1. In fact, they're supposed to be representing all of the real numbers between 0 and 1. Since we're dealing with real numbers between 0 and 1, they have decimal expansions that start with 0 point something, right? So I have used the notation here with the double indexes on the a's to express each of the decimal expansions of these numbers. And remember, since g is onto, I basically have, by assumption, a full listing of the numbers in between 0 and 1. Okay, now here we're going to derive a contradiction. What we're going to do, and this is why it's called a diagonalization argument, is we're going to focus our attention on the diagonal of this lattice. So we're going to look at the first decimal place of the first number, the second decimal place of the second number, the third decimal place of the third number, and so on, like that. So these are all numbers between 0 and 9, right? What I'm going to do is I'm going to define a number. So I'm going to define a real number b that is in between 0 and 1. In other words, it's in the codomain of this function, the range of this function, that is not equal to any of the an's that I have listed. And that's going to be our contradiction because, again, by assumption, this should be a full listing of all the numbers. How am I going to define this b? I'm going to define this b by carefully inspecting the diagonal. Here's how I'll do it. I'm going to define b by defining its decimal expansion, and the goal is to make b not equal to any of the an's. So I'm just going to take, as I define the decimal places of b, I'm going to ensure that b couldn't possibly be equal to any of the an's as I go. So for example, if I take a look at a00, that's some number between 0 and 9, right? Why don't I just define b0, the first decimal place of this number b that I'm defining, to be something different than a00? So like if a0, the number starts with 0.1, then I'm going to start my b number with 0.2, right? Then regardless of what happens after that, I am absolutely sure that b is not equal to a0. And then in the next stage, I'm trying to define the second decimal place for b. I'm going to come and look at a11. Let's say a11 is 5. Well, then I'm going to make b1 not equal to 5. It doesn't really matter what I make it. Maybe I'll make it 4 or 9 or something. I'm just going to choose some number here that is not equal to a11. In doing that, I have ensured that b could not possibly be equal to a1. And then I continue in that process. So here's one way to get that done, like with one fell swoop. Okay, so this is just one option for how I can do this. As I traverse down the diagonal, I just ask myself a question. Is a00 equal to 1? Well, if so, then make b0 equal to 2. If not, if it's something else, like 6, then make b0 equal to 1. And so what I'm going to do then is define this number b, which has just a bunch of 1s and 2s in its decimal expansion. And each one of those 1s and 2s was carefully selected so that, for example, b4 does not look like a44. So that makes b not look like a4. Okay, so what have I done? I have found an element of the codomain, b, and b is not equal to an for any of the n's in the domain. In other words, b is not equal to g of n for any n in the domain. What I found is a b that is not in the range of the function. I have concluded that g is not an onto function. So to recap, we supposed we had an onto function, we got a contradiction, so that proves that there is no onto function from n into 0, 1. And from that I'm concluding that the cardinality of 0, 1 is strictly greater than the cardinality of the natural numbers. And of course, there are as many, if not more, real numbers as there are real numbers between 0 and 1. So from this, we conclude that R has cardinality strictly greater than n. There's no bijection from n to R. And the language that we're using here is that R is uncountable. So the real line is uncountable because it is not countably infinite, nor is it finite. Okay, here's another argument that there are multiple infinities. So like right now I have this countably infinite size that an infinite set can take, and we have this uncountable size. But is that the whole story? This theorem right here, which is proven also by contradiction, it's a nice argument, immediately gets us like this infinite list of infinite cardinalities, which is kind of cool. So like, take a look at the statement. I'm going to argue that any set has cardinality strictly less than its own power set. And this is obviously true if we're talking about finite sets, right? Because in finite sets, we know that the power set has cardinality 2 to the n, where n is the cardinality of the set, right? So obviously 2 to the n is bigger than n, so this result is true because this is a statement about numbers. But what we're saying here is there exists an injection from x into the power set, but there does not exist a surjection. So there is a one-to-one map, but there is no onto map. So this is a statement about maps. Let's prove it. So step number 1, I'll prove that there's an injection. All right, I'm going to define a one-to-one map from x into the power set, and it's going to be defined this way. Take your element of x and output the set that contains that element of x, that element x, and that element x only. Well, f is one-to-one because if two outputs are equal to each other, so if f of x equals f of y, as I've written here, then we're saying this set that has x in it is equal to this set that has y in it. Well, that means that x has to equal y, right? So that's an argument that this is a one-to-one function. What I want to argue now is that there is no onto function from x to the power set of x. So let me suppose by way of contradiction that there is. Okay, we're going to derive our contradiction by defining a subset of the domain in a very clever way. Okay, so this is a little bit tricky definition, so let's go through it slowly. We're going to gather together a certain collection of elements in the domain, but I might want to draw a little picture to sort of understand what it is that I'm doing. So let's imagine that x was the set that had the number 1, the number 2, and the number 3 in there, right? Then what would the power set look like? Well, the power set's got the empty set, it's got all the singleton sets, and of course this is a finite set, x, so everything's super obvious, but I'm just drawing this so that we get a feel for what's happening. Then we have the full set x over there as well. Okay. So g is some supposed onto function, which pretty much seems ridiculous here, but pretend that I've got this supposed onto function drawn. I'm about to, like I said before, cleverly define a specific subset of the domain. And what I want it to be is I want it to be all of the elements of the domain that do not get sent to sets that have themselves as elements. So like, look, the domain element 2 gets sent to the empty set. Is 2 an element of the empty set? No, so circle it. 3 gets sent to singleton 2. Is 3 an element of that set? No, it's not, so circle it. 1 gets sent to the set 1, 2. Is 1 an element of the set? Yes, it is, so don't circle it. So I want to define y to be all of the elements of x such that g of x contains x as an element. I should write that in another order. X is an element of g of x. See, this looks awkward right here, but think about what the function g does. G of x is a subset of x, right? G of x is an output of this function. It's an element of the power set. It is a subset of x. So either x is in there or it's not. Like over here in the picture, 2 is not in g of 2. 1 is in g of 1. To be clear, g of 2 is the empty set, g of 3 is singleton 2, that's what the arrows are saying, and g of 1 is 1, 2. So only these two x values would satisfy, oops, I'm supposed to put not. There we go, not. These two elements are not in their corresponding output sets, like that. Okay, so this is my cleverly defined subset of the domain, right? Y is a subset of X. And being a subset of X also makes it an element of the power set. That's a good thing to observe, right? Note, Y is an element of the codomain. And my claim is that Y is not in the range of G. And that will contradict the fact that I'm assuming G is an onto function. So let me prove this claim for you. Okay, so suppose by way of contradiction that you found a domain element that gets mapped to this specially defined set Y. I'm going to split into two cases and prove to you that that couldn't possibly be the case. So case number one, let's suppose that this magical element X that supposedly gets mapped to Y is in its G of X set, right? G of X is the set Y. X is either in there or it's not, right? Okay, so first case, X is in the set Y. X is an element of X, Y is a subset of X, X is either in there or not, right? Well, let's see here. If X is in Y, that's the same thing as saying X is in G of X, then let's take a look at the definition of Y. Y is exactly those elements that are not in their G of X's. So I conclude from this that X is not in Y. What? X being in G of X is literally the same thing as X being in Y, because G of X equals Y. And yet, X being in G of X is the opposite of what it means to be in the set Y. So X is not in Y. This is clearly a contradiction because X can't both be in Y and not be in Y, all right? So that case is just ridiculous. It can't be the case that X is actually in G of X. So it must be the case then that X is not in G of X. That's literally the same thing as saying that X is not in the set Y, because again, Y is supposed to be G of X. All right, let's come back up to the definition of Y and see what we conclude from that. X is not in the set Y. All right, so X did not meet this condition right here. Otherwise, it would be in Y, right? So X not being in Y means that X must be in G of X. Uh-oh, that's a contradiction as well. Because I started with X not being in G of X, and I concluded that X must be in G of X. So again, this proof by contradiction is a little bit subtle. I should make a conclusion here. So G is not onto. So like we had an injection from X to the power set of X, and we ruled out the possibility of there being an onto function from X onto power set of X. So I conclude from that that the cardinality of X is strictly less than the power set of X. And again, this whole contradiction here with the cases is a little bit hard the first time you see it. I do recommend kind of thinking through it on your own several times before it might sit well with you. But what do we get from this observation? What we get is an ever-growing tower of different types of infinities, right? Because, let's say you start with the natural numbers. We know that the cardinality of the power set of the natural numbers is then strictly bigger, right? But you could take the power set of natural numbers and get yet a bigger set, right? And you can keep doing this over and over again, creating these larger and larger and larger sets. And in effect, you're creating larger and larger notions of infinity.